this is just going to be like a quick, try to be super quick kind of review. Okay, simple harmonic motion was like this. When we had the block, okay, and there was some equilibrium position, and then you stretch it some amount. Sorry, I guess I'm trying to get to the center here, but you stretch it some amount, you do the equations of motion. Essentially, you get that if there's only a restoring force from the spring, sum of the forces is negative kx, which is equal to m times the acceleration, right? Mass times acceleration. And we said that whenever you have an equation that looks like this, or if you rearrange it just a little bit, whenever you have anything that has this structure, the variable, the negative of the variable is equal to its second order derivative. The solution to this, its behavior is going to be some sort of cosine, some sort of sine function or trigonometric function. This will always be the result. There will be some amplitude, and pretty much just, I mean, like this. Like, you can have the phase shift if you're tracking it at a particular time. So I guess in the most general sense, you can say it's like this. But there's some angular frequency, and that natural angular frequency is the square root of that coefficient. It'll always work out that way. Okay. We were looking at, there's two other kind of scenarios, or three, I guess I should say, that you may come across on this AP exam. There's a pendulum, and sometimes what's called a physical pendulum. So the pendulum on the left is going to be like your, I'm going to put in parentheses, ideal. An ideal pendulum is one where all the mass is concentrated on the thing that's bobbing. Okay, when we talk about pendulum, that's something that looks something like this. And if you guys were doing the practice multiple choice or practice AP exam that I gave you last time, the mechanics one, you probably saw a couple questions like this where it's going to swing. Okay, it has some length L. At some moment, it is some angle theta. Your angle is a function of time. All the mass is concentrated at the end, right? And as it swings through this angle theta, it's also swinging through some arc length S. Okay, and if you do the free body diagram on this mass, you have tension, you have gravity, and that's it. Right? And if you kind of break it down, this gravity, there's a component that is in line with tension. This is the, as the book says, the radial component. That should, I know actually the way I drew it, it looks like tension should be greater. It's not. They should be the same length. So they should be about the same length. And then there is this kind of a component of gravity that's bringing it towards the center, right? And if you look at the way it will work out, gravity is always going to kind of bring it towards the center, right? So this is like your tangential component of gravity. Okay, so we sum our forces. If we look at only in the arc length direction, this is going to be a little weird. Not really looking in the direction of x or y, but imagine that you have an axis that is always following along S. Okay, what is the force only along S, or the tangential force? The tangential force is always just going to be gravity. And that component is going to be, if that's theta, right, if that's theta, it's going to be the sine of theta that is always bringing it towards the center. So you're going to get something like this. Oops. Okay. Now the masses cancel out, so we have something like this. Sorry, I'm going to put the physical pendulum on the right-hand side in a second here. So you get negative g sine theta. And this is going to happen a lot. For a pendulum, if it is a small angle, okay, as long as it is a small angle, and what we define as a small angle is if theta is about less than 10 degrees, then we can use a small angle approximation, which is that sine theta is approximately theta. If your theta is in radians, okay, if it's in radians, it's pretty close. So we then argue this. Okay. Now, it's almost like this structure, but not quite, because these are matching variables, and these are not. This is theta, but that's s. This is an angle, but that's arc length. But there's a relationship between angle and arc length, and that is that s equals to theta r, right? So in this case, you bring them both together, you get d squared s dt squared is equal to a negative let's see, sorry, g over L S. L is R, yeah. R would be whatever the radius is, right? And so in this case, for the sweep that it's making, that's L, right? So now we have that form, we have that structure. So the solution is, again, going to be some sort of cosine thing. In other words, there is a linear restorative force. Okay, we kind of call this linear restorative force. Okay, so this natural angular frequency, okay, it's, remember, we gotta be careful, this is not F, it's different from F, this is omega. This is then going to equal square root of g over L. So we can figure out how frequently it's going to swing back and forth. We can figure out what the speed is going to be, what the acceleration is going to be. We can figure out all that kind of stuff. Okay? So that is for an ideal pendulum. An ideal pendulum is where all the mass is concentrated in one spot. All right? So the kind of questions that you'll get on the multiple choice question will be like, what if I double the mass on the end of this block? Well, how will the period change? How will the frequency change? How will it change? Let's say I double the mass. How does the frequency change? Yeah. Sorry, Amuk, were you? I don't know if you're.
Would there be an initial position?
Yeah, there will be some initial position. Usually, wherever you start, that's going to be your maximum amount, unless you like flick it upward or something. I wouldn't put it past College Board.
So how would you account for that initial level?
So then that would, you would look, so at starting position, there's going to be some gravitational potential energy, and if you flick it, it's going to have some kinetic energy. And so then at the maximum, it'll be all gravitational potential energy, so you can figure out how. Yeah, you want to do conservation of energy to figure out how high it's going to go.
But would you make it as a function of time? So, or would you model the
It would.
total, would you model the total arc length, or the total position, or would you have it as the position after it's reached?
You can always create the function at its maximum, or you can do a phase shift. But I think it's easier to just say, okay, if it starts here and I flick it upward and it's going to swing upward, what's the maximum distance it's going to be?
Okay.
Find out that maximum distance, then it's going to be maximum distance times cosine. Yeah. So one of the interesting things and important things to understand about physical pendulum is that, or this pendulum, is that the frequency doesn't depend on the mass. Okay, it seems kind of weird, but it doesn't depend on the mass. And the important thing to realize about that, why does it not depend on the mass? Because gravity depends on the mass, but its inertia also depends on the mass. And so they cancel out. kind of like when we were looking at how a ball rolls down a ramp. The mass doesn't influence the speed at which the ball rolls down the ramp or the cylinder or whatever. It's the shape. The shape affected it. So in the same way, the mass doesn't actually influence the rate at which a pendulum swings. So in fact, usually you want to use a pretty heavy one so that you overpower any sort of friction. So the only things that actually influence the period or the frequency is the acceleration due to gravity. So sometimes they'll say, okay, let's say you take a pendulum and you're on Earth and then you go to like Mars or something like that, right? How does that change your frequency? Or you might have a different length. Okay, the longer the pendulum, the longer the hold on, let me think. So the longer the pendulum. Wait, something that makes sense about that. That's a smaller number. Huh? No, the frequency is still just as it is. Huh. Yeah, it's just the coefficient, the square root of that coefficient. I'm positive. Longer period. Yeah. That makes sense. Sorry. I was having a brain fart. The longer period should have a lower frequency. That makes sense. It doesn't swing as many times per second. Or alternatively, the longer the pendulum, the longer the period, the longer it takes. And that should make sense. Okay. A physical pendulum is one where you have a rigid body that is shaking. Okay. Something like this, where you have to take into account that the whole thing is pivoting. This is where it gets a little tricky because you're not looking at a force on just one object. You got to look at the torque on the whole thing. Not too worried about all of the stuff that's going on here. I think it doesn't show up in your equation sheet either. The only thing you really need to memorize that's useful is that for a physical pendulum, what does a physical pendulum look like? It's, well, doesn't quite look like this, but when it's talking about a physical pendulum, it's just talking about some rigid object, full rigid body that's rotating. So you got to deal with torque. And there's some pivot and some length. Chris?
I was going to ask what the pivot was. So is it all the way at the top?
It doesn't necessarily have to be. So
if it isn't, does the amount of mass above the pivot also matter?
No, because and again, this gets pretty complicated because I think the shape doesn't particularly matter. In the end, the way the shape works out is in the moment of inertia. Oops. The moment of inertia determines, or is how your shape influences the period. L is the distance from the pivot. So that it doesn't have to be at the top. It's just how far is the pivot from their center of mass. So as long as you know where the center of mass is, and you know how far it is from the pivot, and you know the moment of inertia, then you can figure out what that natural whatever frequency is going to be. So this one is kind of a good one to memorize. That's MGL over I. Okay. It may seem kind of weird that like the further it is away from the pivot, the faster it'll rotate, but that actually is hidden in this moment of inertia. The assumption is the further you are from the pivot, well, your moment of inertia is going to be bigger too. So the net effect of that is actually going to be that it should be slower the further you are. Yeah. This I be careful, this I is not the moment of inertia around the center of mass. This is I around the pivot. Not the center of mass. So you'll have to do parallel axis theorem. That may come up. Okay. Still remember that? Parallel axis theorem? Going way back to December? Way back, throwback. All right. Okay, so we looked, there's a particular circuit that behaved like all of this. What was that circuit? LC? Okay, LC. The LC circuit, the inductor capacitor circuit, had this oscillatory motion, or not motion, but behavior. Yeah, take some time, try to sort all that stuff out. Yeah.
So, can you remind us of parallel axis theorem?
Yeah, parallel axis theorem was that if you want to know the moment of inertia around some pivot, you take the moment of inertia around its center of mass, then you add to it the mass times, sorry, let me not use R. Let me use D. Yeah, let me use D. MD squared, where D is the distance between pivot and center of mass. So I guess if I were to be consistent, it would be what L represents here. But yeah, parallel axis theorem was just like if you shift the pivot away from the center of mass, you add a very specific amount of moment of inertia. Okay. Okay. That's it for simple harmonic motion. That's all chapter 14. So hopefully what I really want to do is before AP exam, we can get through like 2 or 3 practice exams. I don't care particularly that you guys do it in a timed fashion. You're welcome to try and do them in a timed fashion. I think it's really a better use to just review all the different kinds of material that we've covered and the different ways they'll ask those kinds of questions. It's kind of a good way to check for any holes in your knowledge. So we will see these kind of problems and then we can kind of talk about them. Okay. The last, I know I keep kind of saying this like we're right at the end, but this really is the very last thing. Okay, chapter 34. We're done with 33. 34, there's only one thing in here that is important to bring up, and that is Maxwell's equations. So here's the thing. Between Coulomb's law and Faraday's law, or sorry, I guess Gauss's law, and then you have Biot-Savart law and Ampere's law and Faraday's law, all these different kind of descriptions of the nature of electricity and magnetism. One guy, fate have it, took all of it and just put them all together and said, these are the laws of electricity and magnetism. And he wrote like a couple equations to represent all of it. Right? He combined everything and summarized it, and basically explained everything there is to do with electricity and magnetism. Like, as far as we know, this is like the complete explanation of it. At least electric and magnetic fields. Okay, that's not to say he explained electrons and protons, the particles themselves, or this isn't really to say that he figured out the origins or the reasons why these things happen. He came up with the equations that explain, that help you predict the behavior. Okay, so this all explains the behavior, but not really necessarily why or what it is or why it is and that kind of stuff. Okay, let's take a look at these. These are Maxwell's equations in integral form. So take a look at the first one. First one should be super familiar. Gauss's law is essentially Coulomb's law. Okay. Now, actually using Gauss's law We usually require a high amount of symmetry to actually use it, to make calculations with it. But technically within Gauss's law is Coulomb's law. Okay, so it just says that electric fields are created by charges. That's really what it's saying. When you look at Gauss's law for magnetism, what it's saying is that you can't get magnetic monopoles. For some reason, magnetic fields always occur in loops. Faraday's law says that you can create electric fields by changing magnetic fields. Okay? You can create electric fields by changing magnetic fields. Lastly, Ampere, now this one is a little different. This is the Ampere-Maxwell law. We saw this part that said that a current can create a magnetic field. This is something new. Okay, this is something new. We'll look at that in just a second. And then lastly, this is what, by combining the forces from electric and magnetic fields, we call this the Lorentz force. A Lorentz force is the force from taking Coulomb's, whatever, QV cross B and Coulomb's law put together, or not Coulomb's law, I guess the Coulomb force, putting them together and creating one equation for the force from either electric or magnetic fields. And that is the Lorentz force. Okay, so at this point we talked about all of these. There's a lot of, I know this looks simple, but well, it's very concise, but there's a lot that goes into these, right? The Biot-Savart law is kind of hidden in Ampere's law. Okay, it's hidden in there because we said that Biot-Savart law was a moving charge creates a magnetic field. Well, currents are moving charges, and so this, kind of like how Gauss's law is another way of restating Coulomb's law, Ampere's law is kind of another way of restating the Biot-Savart law. Okay, but this is totally different. This is saying that a changing electric flux can also create a magnetic field. Okay, and we haven't explored that yet, so let's take a look at that for a second. Where did this come from? This is what we call displacement current. Okay, and it comes from this. Imagine you have a capacitor that you're charging up or discharging. See, now if you're charging it up or you're discharging, in the wire there's current going through the wire. So we would expect there to be a magnetic field around the wire. But the question is, would there also be a magnetic field between the capacitor plates? Because there's no actual charges moving from one plate to another, but the assumption about Ampere's law was that if you have a circuit, or if you have current flowing, right, you got to have some sort of circuit, right? And a capacitor kind of seems like it's not actually a circuit because you got this gap. So the way the book kind of goes around explaining that is, when you do your Amperian loop and you look at the surface that is enclosed by your Amperian loop, it doesn't necessarily have to be a perpendicular surface. You can use whatever surface you want. If you, for most scenarios, if the current goes through that surface, it will go through any surface that you make, right? If it doesn't go, if the net amount of current going through the surface is 0, no matter which surface you choose, that net current should be 0. Or if there is a net current going through one surface, there should be a net current going through any surface, except for if you use a capacitor. A capacitor seems to defy this. And so what we analyze from here is that, well, there may not necessarily be a current of charge going through your capacitor, but something is happening in order for there to be a current through this whole system. In order for there to be a current going through the system, the capacitors must be charging or discharging. That means they must be building up electrons or charge or losing charge, which means that the electric field between them must be changing in time. And so if you go through some of the math, essentially what they do is they find that there's kind of an equivalence between the current and the rate at which that magnetic field is changing. Or sorry, not magnetic field, electric field. There's this relationship between current and changing electric field. And so we generalize that and we call that a displacement current. Now, I don't think they have this in the equation sheet either. So I haven't honestly seen too many questions about this on the AP exam. Only very conceptual questions, like what is displacement current or how's it created. In a very general sense, you just need to understand that a displacement current is when you have changing electric flux. So it's really important though, because when you take a look at amperes, this Ampere-Maxwell equation, and you compare it to Faraday's law, they provide a perfect symmetry between a changing magnetic field creates an electric field, and a changing electric field can create a magnetic field. So they really are important because these two parts, Coulomb's law or Gauss's law, says that charges create electric fields. And the Ampere part of Ampere-Maxwell's law says that moving charges create magnetic fields. So charges create these fields. But the other two parts say that you don't even need charges to create these fields. These fields can kind of create themselves, which is a completely in the absence of any charge, they can create these fields, which is how we get light and radio signals and all that kind of stuff. Okay, so in terms of the actual calculation, you would approach the calculation pretty much exactly the same way, except for one detail. In Faraday's law, it's negative, so a changing magnetic flux induces an opposite direction electric field. Opposite to your right-hand rule. But this displacement current is in the same direction. Okay, so there's kind of a good diagram of this right here. Okay, so for example, you have this solenoid. If you have increasing magnetic flux into the page, it creates this reverse electric field, right? The electric field is induced to kind of oppose that magnetic flux. In a displacement current, it follows the right-hand rule. Okay, so you can kind of follow this increasing flux into the page for magnetism. Your fingers would want to go clockwise, but the electric field is counterclockwise. That's the negative part. Yeah. But for the Maxwell part of Ampere's Maxwell equation, or Maxwell law, increasing electric field into the page does create a magnetic field clockwise. So it actually follows it. So right-hand rule for the Ampere-Maxwell law, but then negative right-hand rule for Faraday's law. It's kind of funny. I was talking to Wyatt the other day about how confusing magnetism is. It just is. It's just the way nature is. It's really weird. And if you think this is weird, go try and study quantum mechanics. Quantum mechanics makes no sense whatsoever. Even like Richard Feynman and all like the greatest minds are like, if you think you understand quantum mechanics, you probably don't actually understand quantum mechanics. Like that's the thing. So physics is just, it can be really, really strange, especially when we talk about electricity and magnetism. And I think hopefully mechanics isn't too bad, but okay. So thus concludes everything.